Where we finished our last set of PowerPoints, we were finished with the Bohr model of the atom. The Bohr model was a good model for describing hydrogen, but we need a little bit more. So we're moving on to the more modern model of the atom that you probably have not been exposed to prior to this class. This is the wave mechanical model, also known as the Schrodinger model, named after its developer, Erwin Schrodinger. So Niels Bohr had a problem, and his problem was that we have a large number of elements. 118 are known now, and his model worked essentially for one element, which was hydrogen. It also worked for other elements or ions as long as there was only one electron present. If there was more than one electron present, then the model would not work. So we need something more. So if we go back and think about some of the things that we covered in the previous lesson, we had Max Planck, and Planck made the discovery that light had both properties that are unique to waves and particles. And by having two sets of properties, we have what we would call wave-particle duality. Duality refers to two, and wave-particle would be the two. So at some times light behaves wave-like, and at other times it behaves particle-like. In most cases it's wave-like through space, but it's particle-like when it interacts with matter, such as during photosynthesis. Following Planck, we have a Frenchman, Louis de Broglie, or sometimes you'll just hear me say de Broglie, but it's actually probably Louis de Broglie. He made a statement. Basically, he was looking for a topic to study for a doctoral research project. If light, which is normally thought of as wave-like, can have particle properties, he asked the question, could the particle, a small particle like an electron, have wave properties? So he basically flipped the issue that Planck found. Planck found that light can have both particle and wave properties, and Broglie was interested in whether or not a particle, such as an electron or a baseball or anything, could be found to have wave properties. And he thought about this, and he was a theoretical physicist. After a detailed analysis of the math surrounding the electron as well as particles at the time and waves at the time, he proposed that electrons and other particles can have wave properties. And as a result of this, he developed an equation. The equation looks like this, where we would say the wavelength is equal to Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, divided by mass of whatever particle it is that we're looking at. In this case, it would be, for instance, the mass of an electron, and this is the speed of light. Which we will take to be 3.00 times 10 to the 8th meters per second. So if we wanted to use this equation to calculate something, we could calculate the wavelength of an electron traveling at 75% the speed of light. So we would have the wavelength of the electron, I'll put it as lambda E minus, equals h over mass of the electron times c. This is going to be equal to 6.626 times 10 to the negative 34th joule seconds divided by the mass of the electron, which is 9.11 times 10 to the negative 31st kilograms. It does need to be in kilograms. And then the speed of light (3 times 10 to the 8th meters per second). Make sure you have the speed of light and the mass of the electron as well as Planck's constant written down in your notes so that you can refer to your notes to get these values. And we get an answer of 2.42 times 10 to the negative 12th. And this is a wavelength, so the answer would be in meters. This seems to be a rather short wavelength, but let's calculate the wavelength of a ball that has a mass of 0.250 kilograms traveling at a speed of 1 meter per second, something like a softball maybe. So we can say the wavelength of the ball is equal to Planck's constant over the mass of the ball times the velocity of the ball. Notice here I'm using v instead of c because c is the speed of light, whereas v is going to be the speed of the ball. So this is going to be 6.626 times 10 to the negative 34th joule seconds divided by 0.250 kilograms. And the speed of the ball, 1 meter per second. And our value, 2.65 times 10 to the negative 33rd meters. Okay, now, the biggest thing to get from this is that when we have something that's very small, like an electron, compared to something that's relatively large, like a softball, we can see that when we're looking at the magnitude of the scientific notation of the wavelength, 10 to the negative 12th is a small number, but it's huge, tremendous compared to 10 to the negative 33rd. So large objects have very small wavelength. Smaller objects, like electrons, have wavelengths that might be significant in terms of the size of what they're moving in. This electron is limited to the diameter of an atom, so this wavelength is actually approaching the size of the diameter of an atom, whereas if you're a softball player, you don't have to consider a wavelength this small. As the ball comes towards you, you don't have to take that into your calculations as a pitcher or a batter in terms of trying to hit the ball. It's so small. But it does have a wavelength that you could calculate according to the de Broglie equation. So what this does, though, is one more thing, is it provides us with something known as the wave-particle duality of nature. The last time I said wave-particle duality, it was wave-particle duality of light. This is of nature. All objects have wave and particle properties. So even great physicists have problems in terms of their ability to think through some of these things. Bohr treated the electron like it was a particle because that's the way we had thought of electrons, and we still do it sometimes, think of electrons as particles. He didn't think of the electron as a wave at all, but have it being strictly matter. With that, he was able to calculate with his equations things like position, momentum, which is mass times velocity. And he said that both of these values, the position and the momentum of an electron, could be known precisely. An electron, however, if you consider an electron as a wave, not a physical object, it loses this precision. You can't know exactly where an electron is or its momentum with great precision. And the more you know about one, it comes out is the less that you know about the other. We'll see that in just a moment. Okay, so you cannot know exact location and momentum of a wave. This created some big problems for physicists because physicists like to be able to make predictions, for instance, about the way the world works. And here we're saying that we can't know exactly where an electron is or how it's moving. So enter our next scientist, Werner Heisenberg. And Heisenberg developed a mathematical theory that says it's impossible to know the exact position and momentum of an electron simultaneously. So this was implied by the idea that an electron was a wave from de Broglie. However, Heisenberg developed the math around it, showing that that was exactly the way it should be predicted, that electrons have a lot of statistical nature in them, and that we can't know exactly where they are and what they're doing at a given point in time. He wrote an equation which looks pretty bad, but it's what this is. Delta x is the uncertainty in location, and this is delta p is the uncertainty in momentum. And this, of course, is Planck's constant over 4 pi. But this is, we can just say that this value out here is a constant, because we've got a constant, Planck's constant, divided by 4, which is a constant, and pi, which is a constant also. So what this is saying is that the product of the uncertainty in the location of an electron and the uncertainty and momentum of an electron is going to be greater than or equal to a certain value, a constant value, h over 4 pi. Now, one way to look at this is to look at momentum as mass times velocity. So we can say delta x equals, or excuse me, delta x times m delta v, which is momentum. And we can see that, let's just make this equal to a constant for discussion purposes. As the uncertainty in location increases, that means the uncertainty in momentum has to decrease, okay, for this to remain constant. And likewise, if this decreases, then this is going to have to increase for this to stay constant. Now, let me erase a little bit here. Another interesting point is, and it sort of relates back to the way things really work, if we have a very small mass, if mass is small, then even moving it close to the speed of light, this value can be a very small value. So if we have a small mass, the uncertainty and momentum is small, or the mass is small, and that's going to actually make this to be a small number. But for this to be small, this has to be large. So we find that the smaller the mass, the larger the uncertainty in location. We don't know exactly where a small mass is going to be. So for instance, if we have an elephant which has a very large mass, then we can say this value is large, so the uncertainty in where that elephant is very small. We can see where an elephant is pretty clearly. But on the other hand, if we have something like an electron, the mass is very small. If the mass is very small, then that means that the uncertainty in where it's located is very large. So it's we're unsure about where the electron is located exactly around the atom. That's a difficult concept to wrap your mind around, and we're not going to spend too much time wrapping our minds around it. So this is known as Heisenberg's uncertainty principle. We can't know exactly where a moving particle is and exactly how fast it's moving at the same time. We can know one or the other, but we can't know both. And I'm not going to bother going through that, but this is a limit to what can be known about nature. That limit is, as we said earlier, h over 4 pi. So we have a limit on how much information we're actually able to know precisely about the universe. When we get down to a very small level, we can't know things very well. So what Bohr's problem was is that Bohr's equations fail beyond a one-electron atom because they claim to know more than it's possible to know. Heisenberg shows us with his uncertainty principle that it's impossible to know everything that Bohr's equations were claiming to know. So in a lot of cases it works out that theories are considered incorrect or need to be improved upon because they don't know enough information. In this case, Bohr was stating that he knew more than he actually knew, because he was assuming the electron was a particle, which is the way it was thought of at the time he was developing his model. So the best that we can do with the very small is use statistics, probability, to describe atoms. And that was a little bit difficult for physicists to begin with because they'd spent the time up to that point in the history of physics describing nature very precisely, and here we're going to start using this thing that we call statistics to describe atoms. So then we bring in our last genius of the atomic models. Well, I won't say the last genius, but the last major model, and this was Erwin Schrodinger. Left my C out, excuse me. An Austrian. He was able to utilize de Broglie's concept that electrons have wave properties, and he developed a new model. That model, when we talk about models, we're not talking about building models of things like a physical model necessarily. A model in physics is a set of equations usually. So he developed a set of equations, or a model, to describe electrons moving around the nucleus as waves. He included the quantum theory because waves are definitely quantized. They have definite numbers of wavelengths, for instance, and definite frequencies, for instance. And so waves of specific energies and frequencies provide solutions to his equations. So we've got a set of equations, which you're not going to see here. The equations that are behind this model are beyond what you're at this point ready for. In fact, it may be beyond what most people are ready for. It's a very difficult scenario to interpret, but regardless, there are equations and they describe electrons. Okay. The solutions to his equations are known as wave functions, and what the wave function does is gives probability of finding an electron at a given place, or at least it's related to that. It works out that the square of the wave function gives the probability, but it's the probability of finding an electron at a given place. Notice we don't say it's going to be at a certain place, it's just what's the probability of finding it there. And in these equations we have some values that we insert called quantum numbers, which are rather important to us for some reasons that you'll see shortly. Quantum numbers are sets of numbers that describe the location and behavior and also energy of electrons. And they are required to be able to calculate probability of locating the electron around the nucleus. And that's really what we're after at this point, is trying to decide how electrons are actually arranged around the nucleus. There are 4 specific quantum numbers needed to completely describe a single electron. Every electron is described by its own set of quantum numbers. The first of these is the principal quantum number. This was first postulated by Bohr, and this is actually the part of Schrodinger's model that's left over from Niels Bohr. Symbolized by the letter N, and indicates the main energy level of an atom. And we need to talk about an energy level definition. If you remember, Bohr had a nucleus. Let's put a positive nucleus for a hydrogen atom, and then we had these orbits, so to speak, that electrons could be in, and they were definitely in one of these energy levels. Well, we look at things a little bit differently from quantum mechanics or wave mechanics. The energy level definition here is a location of high probability for finding an electron in an atom. Not the only location, but a high probability location. Just a second. So this energy level definition is different from Bohr. Bohr's was a definite orbit for an electron to move, like in a circular pattern. Here we say that the electron is likely to be found in those locations. And you have to think of this as being, for instance, like a three-dimensional space that completely surrounds, like a sphere surrounding the nucleus. And usually we would have a certain probability, like a 90% probability of finding the electron on the surface of that sphere. The values for the principal quantum number are 1, 2, 3, 4, and technically into infinity. So it doesn't end. This is a never-ending model. Physically speaking, probably the highest level is going to be around 7. Oops. Highest value is going to be up around 7, but technically it goes to infinity. So this is a model that can continue to expect more atoms to be found, which is what has happened since Schrodinger developed the model. The maximum value of N for an atom is the highest value that any electron is going to have whenever we're looking at the highest value of N, indicates something about the size of the atom. The higher the value of N, the bigger the atom. It also represents or is related to the period on the periodic table for an element. So, for instance, if you have your periodic table out and you find potassium, remember the periods are horizontal rows. And if you look at the periods, there are 7 periods. And it works out that whatever period an element is on is the highest value for an energy level that's needed for all the electrons in that atom. So, for instance, potassium is on period 4, K is on period 4, therefore it requires 4 energy levels. Hydrogen, to take care of its 1 electron, hydrogen is on period 1, it needs 1 energy level. Sodium is on period 3, it needs 3 energy levels. So there's a definite relationship here, and this becomes very important because the Schrodinger model is very closely related to the structure of the periodic table. The maximum number of electrons that can fit on an energy level is 2 times n squared. Okay, and you've probably, if you think back, I know it's been a while, but if you think back to physical science, you might have heard things like the first energy level can hold up to 2 electrons, the second energy level can hold up to 8, the third can hold to 18, and so forth. Well, if you plug in the number of the energy level into this equation and square it, then multiply by 2, that will tell you how many electrons can fit. So, for instance, on the 4th energy level, we would have 2 times 4 squared. 2 times 4 squared is 16 times 2. So you can fit up to 32 electrons on the 4th energy level. And that would work for any of the energy levels of the atom. Just plug in the energy level here, calculate the number of electrons that can fit. Doesn't mean that there will be that many electrons, that's just a maximum. All right, so summarizing, the value of n, the principal quantum number, tells us the main energy level that we're dealing with where an electron is likely to be found. It has numerical values that go with it that are always whole number energies, 1 to infinity. There are no fractions, there are no negative numbers, and 0 is not an option, so 1 is the lowest value. We can also say, for instance, that if you remember the terms from the Bohr model, excited state and ground state. For ground state, an electron's in its lowest possible energy levels. So if we're looking at, or if we have 40 electrons, then all the electrons would be as low as they can go. When we want to find the maximum number of electrons, or maximum value for n, we're thinking about a ground state atom, and we would say that if we've got a certain location on the periodic table, we can get the maximum number of electrons in the number of energy levels that equals the period that the element's on. So again, as an example of that, sulfur, for instance, is on, if you find that one, it's on period 3. Therefore, it's going to have 3 energy levels to take care of all of its electrons, but specifically in ground state. We also have excited state, where the electrons can move to higher levels, something higher than ground. Okay, so the second quantum number is known as the angular momentum quantum number, and is represented by the letter L. This is an L. The font makes it look like a 1, but it is L. And it indicates a couple of things. First of all, it indicates the energy sublevel. An energy sublevel is a region within an energy level with high probability of locating an electron. That would be the definition of an energy sublevel. That made me think of something else that I should put in here. I'm going to go back a slide for just a moment. Sometimes when we say energy level, another word for that you'll sometimes see is shell or energy shell. So this is a shell. If that's a shell, then we could also call this a subshell. In case you see that term, it's the same thing. It also specifies the shape of an orbital, and it also gives us the number of sublevels per energy level. The number of sublevels in an energy level is equal to the energy level number. So in the first energy level, there's 1 sublevel. In the second energy level, there's 2 sublevels. In the 4th energy level, there's 4 sublevels. In the 7th energy level, there's 7 sublevels, and so on. Okay. These sublevels are represented by letters. We're only going to need 4 of them. There are more, but those are S, P, D, and F. And as far as energy is concerned, the order of the energy for sublevels is always S to P to D to F if everything else is the same. So in the 3rd energy level, the S sublevel is lowest in energy, the P is next in energy, and then the D is going to be the highest energy sublevel. So if an energy level has all 4 of these, then S is going to be lowest, P is next, D is next, and F is highest in energy for the electron to be located in that space. So let's look at sort of sorting some things out a little bit. In energy level 1, we're going to have one sublevel. Its name is S. And S sublevels, let's add a shape to this. S sublevels in general have a spherical shape. Energy level 2, I didn't mean to put 3 down, but we'll just go with it. Energy level 2 has 2 sublevels. Right here. The S sublevel and the P sublevel. General shape of an S sublevel again is a sphere, and the P is going to have, if this is the nucleus, then we have areas like this on either side of the nucleus. And to differentiate between the S on energy level 1 and the S on energy level 2, we normally put the energy level number in front of that. So we have the 1S sublevel, the 2S sublevel, and the 2P sublevel. Energy level 3, we have 3 sublevels. We have 3S, 3P, and 3D. S, of course, is a sphere. P is this, I always call it a peanut shape. And then D sublevels have all sorts of things that can result, such as, I'll show you some shapes of these on graphics later, but we may have like 4 lobes. We may have a lobe above, a lobe below, and sort of a donut-shaped area around. So there's multiple shapes that we get from these. And I don't know if I put energy level 4 in or not. I did. This would be 4 sublevels. And as far as the names of the sublevels, it would be 4S, 4P, 4D, and 4F. And shapes are the same, and I'll show you some Fs later. When we get to D and F, the shapes get rather complex, difficult to draw. And let's move on to the magnetic quantum number, which is symbolized by the letter M. The magnetic quantum number represents the number and orientation of orbitals in three-dimensional space. And so that means how many orbitals are present, and also how they're oriented around the axis. Now, let's talk about orbital for a moment. An orbital is a region within an energy sublevel with high probability of locating an electron. Okay. The level M defines the number of electrons per orbital, and any orbital, regardless of the type, S, P, D, or F, is going to have 2 electrons max. That is a max. They can have 1, they can have none, but they cannot have more than 2 per individual orbital. Now let's go through and list the energy sublevels, levels, sublevels, and orbitals.